Okay, let us get started. Okay. So we're going to pick up where we left off with Poisson. And if you remember last time with Poisson, we kind of established the relationship between Poisson and binomial. So I'll go ahead and just run that again, Poisson.py. And what we're seeing here is that as we subdivide the number of trials, we're not necessarily changing the expected number of events that occur. And as a result, we're trending the number of trials toward infinity, and that is leading binomial toward Poisson. So we can kind of discover where Poisson comes from with this in mind. To give kind of a visual reference for that, think about a segment of time, and let's say this is 10 minutes. Let's say there's 5 cars that go by every 10 minutes, and this is some road, and the cars are independent of each other, and that looks like it says scars, doesn't it? Let me just make that say 5 cars. So 5 cars every 10 minutes. Now, if we wanted to approach this in in a binomial way, we might subdivide this time, right? And we might think of each minute those very evenly spaced minutes. We might think of each of these minutes as either being a car or no car, right? Or, the way we've been doing it, it's either going to be 0 or it's going to be 1, right? 0 or 1, 0 or 1, and so on. So this is a very binomial approach. We're thinking about in any given minute, there's going to be a car or there's not going to be a car. And so the most cars we can have, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. The most cars we can have is 10 cars. And the least cars we can have is 0 cars. And that's all we can satisfy with this binomial approach. Now, if we subdivide this, essentially what we're saying if we construct it in this sort of binomial way, we're saying that we can have 5 cars, not necessarily in 10 minutes, but in 10 trials. And to trend this toward Poisson, well, maybe, we're going to hold 5 cars constant. This is 5 cars on average, and then we're just going to subdivide all of this, right? So visually, this might be a way to think about it. And then instead of 10 trials, we're thinking 20 trials, right? So 5 cars in 20 trials, and then maybe we subdivide that further. We just keep having this until we are infinitely precise in this measurement. And so now we're at 40 trials, right? We have 40 opportunities. But here's the thing. We can still use binomial to approach a solution to this problem. It's just that we still have discretized moments of time, right? So, we subdivide this. This is going to be in terms of 15 seconds, right? So for any given 15 seconds, we can either have a car or not have a car. And, we could divide that down further to 7.5 seconds and, 3.75, right? Yes. So we can keep going, we can keep having this and having this, and we're going to get closer and closer to the probability, right? We're going to keep getting closer to the probability that would be represented by Poisson. And in some way, we can think about this subdivision as being a better version of binomial, but keep in mind, we're never changing our expectation for the number. And, as we do this, we're essentially causing a decay, and it ends up just being, if you work through the actual derivation of that equation, you can take the binomial PMF and make it into the Poisson PMF through, through trending n toward infinity. It will end up being the Poisson PMF. So that's where we get the emergence of E. And last time I pasted a video of a video that's part of a 4-part series on where does E come from, essentially. What are different places that E can emerge from? And that's just exploring E with code. So we get this PMF at the end of the day, e to the negative lambda times lambda to the k over k factorial. And that's the Poisson PMF, right? So this is the Poisson PMF. All right, so we'll need some code from last time, specifically this little snippet, in case you're starting from a new file. I'm not going to worry about pasting in this, how we can get binomial to approach Poisson. I'm not going to worry about that. I'm just going to leave it in the notes. But I do think it is important to, figure out where some of these mathematical concepts come from, and constants, where those constants come from. So here's the code that we're going to be working from. All right. So we've got this formula. We've got the Poisson PMF. Let's think about this in 2 phases. Let's think about a Poisson phenomenon, what that might be. And this is the one I've been using. So here's a Poisson phenomenon. There are cars passing by an intersection at a certain time of day or year for the duration of a fixed amount of time. Those cars, the number of cars that pass by will likely follow a Poisson distribution, or something close enough to a Poisson distribution that we can try to answer Poisson-like questions. So here is a quick breakout that illustrates that phenomenon. So a given intersection will have, on average, 15 cars pass through in 10 minutes, or min-2a's. What is the probability that 20 cars pass through in 15 minutes? So let's put a timer, and I'm going to actually fix that typo, which I could have done months ago. Yeah, go for it. Okay, let's answer this. Really what we're looking for here is the values of k, the values lambda and k, right? And that's how we're going to think about this. Let me just grab this snippet from up here. I'm going to make this a little bit bigger. Okay, so what is our lambda? What is our k? Let's look at the problem. On average, 15 cars pass through in 10 minutes. What is the probability that 20 cars pass through in 15 minutes? So k is going to be 20. And so how do we think about this? We're dealing with a different amount of time, right? How do we think about that different amount of time? So 15 cars in 10 minutes. What would we expect in 15 minutes, right? So let's start with the lambda we know, the lambda for 15. The lambda in relation to 10 minutes. And then let's think about what the shift is from 10 to 15. Well, we can think about that as being however many times 10 goes into 15, right? And then we can just multiply it. So we can convert our lambda just like that. We can say that lambda is going to be that original lambda, and then we've got this conversion that takes account for time, for the change in time. So let's find out what that is. It looks like that's roughly 0.0769. And this is the kind of thing I would likely round to 3 places or 4 places. Let's do 3. 3 places, 4 places, I think is what I was thinking. Yeah, 0.769. So with any of these kinds of distributions problem, we're trying to consider first, what is the phenomenon, right? The general phenomenon, how do we describe that? What distribution does that follow? And then we're going to try to figure out the parameters that we're passing into the PMF or the CDF or whatever. In this case, there are 2 parameters to the PMF. That is going to be lambda and k, where lambda represents the average number of successes or occurrences. I like thinking about this in terms of occurrences in some volume of time, some area. We can use this for different things. The easiest way to think about it most often, I think, is the average number of occurrences in a certain span of time. Right? So if we change the span of time, if we change this, if we make it more time or less time, we have to change lambda accordingly. But one of the things about Poisson is we assume that we can do that. That's an assumption we make. So yeah, lambda is the average number of occurrences in a certain amount of time or space, volume, etc. So I think there might be a couple more questions like that. Oh, no, I think we'll do a lot more of those questions a little bit later. I'm going to have you code a different function. And this is something I want you to think about, okay? And maybe I'll give you a little more context, right? Lambda sits in some value of time, some span of time. And, if we have a lambda of 5, then we're going to have 5 occurrences. Those aren't very big, but spread out in that span of time. And here's the thing about lambda. We could have this actual average number of occurrences occur, or we could have 0 occurrences occur, or we could have up to an infinite number of occurrences occurring. So just because our average is 5 doesn't mean that we're going to get 5, right? We're going to get 0 or 1 or 2 or 3 all the way up to an infinite number of times. Now, that's obviously impractical for most real-world situations. We're not going to achieve infinity in the real world. But I want you to understand that, whereas the PMF is going to give us the probability of a specific number of occurrences, like what's the probability of 3 occurrences if we expect 5, the CDF is going to give us the probability of, let's say, 3 or less occurrences, right? So it would be the PMF of 0 plus the PMF of 1 plus the PMF of 2 plus the PMF of 3. So just taking that into consideration, I'm going to have you code the CDF function, which is going to be from 0 up until some high value of k. So let's set up that breakout. I'll give you 5 minutes to code this up. I'm not giving you a formula for it because I want you to think about what the CDF actually is, right? Just consider what is a CDF and code that out accordingly. So go ahead and get started on the CDF for the Poisson distribution. So I'm just going to address this question really quick. The units of lambda in the case of the cars problem, I think we ultimately changed to 15 minutes, right? So what we're talking about with lambda is, you know, that statement, 15 minutes times 15 over 10, the units for that are cars per 15 minutes. So that's how we're thinking about lambda. It's you know, the number of occurrences per unit of time, and we only consider unit of time or unit of space or volume or whatever as implicit in the lambda, right? So we don't necessarily need to notate it directly. We don't need to consider time, although in some formulations of the lambda PMF, the Poisson Pmf, they do include time as part of the lambda. You know, they'll break lambda out into a fuller expression, but you know, in general, we're not going to do that. So let's code the CDF. The way that we can think about the CDF is it's accumulating the PMF, right? So that's just going to be a call to the PMF. So this is the Poisson CDF. We pass in lambda, we pass in the high value of k. That's going to be inclusive, right? And then we start at 0, and we can just say for each k in the range of k high, and we'll do k high plus 1. The CDF is going to be incremented by the Poisson Pmf, where we pass in lambda and k, and then we can just return the CDF. So that's, you know, a very basic accumulator pattern to build the CDF. And if you think about it, a accumulator, cumulative distribution function, it's in the name, as we can see. So what kind of question can we answer with this is the real question. Well, I've got a question that we can answer with that, and I'll put that up. And I'll paste this in, right, so that you have it if you didn't get to it. K high is the it's the parameter that it's the way I'm naming the parameter to the CDF. So if we're thinking about getting, you know, what if we're asking the probability of less than 15 cars in 10 minutes, then k high is going to be 15 because we're considering k of 0, k of 1, k of 2, k of 3, all the way up to k of 15, right? So that's why I'm naming it k high, and really that's for my own convenience, because then I can just pass k in right here, right, to the Poisson Pmf as we accumulate into the CDF. So let's look at a worked problem that I have here, and we'll take 3 minutes on this. So a given intersection will have on average 15 cars pass through in 10 minutes. What is the probability that more than 15 cars will pass through in 15 minutes? So I'll set the timer and go ahead and solve that. This is a CDF kind of problem. Here, let's pause for a second. And it looks like there's a fair amount of confusion around the construction of lambda. And I think I can clear that up. So in that first, where is it? It is right here. Okay, let me pull up the other the earlier problem as well. And these are kind of two different versions of the same question. So I think this can be helpful. Okay. So a given intersection will have on average 15 cars pass through in 10 minutes. What is the probability that 20 cars pass through in 15 minutes? Let's look at this like so. Okay, so we've got 10 minutes. If we've got 10 minutes, excuse me, and we have a lambda of 15 in 10 minutes, then how do we calculate the lambda for 15 minutes, right? So this is, I'll say lambda sub 10. What is lambda sub 15? Well, 15 minutes is longer than 10 minutes. And a way that we can think about this is that if we think about 15 as being 15 times 10 divided by 10, right? Or 15 times 1. Then we can think about a lambda in 15 minutes, right? Because this 15 is related to this span of time. If we want that to relate to this span of time, well, how much have we altered the span of time? We've actually altered it 15 over 10 times, right? So we want to consider how many times 10 goes into 15, and then we can just multiply that by 15 to get our lambda. So here's our original lambda right here. We're modifying that for this longer span of time, this lambda sub 15. Does that kind of clear up what's happening there? No? Let's think about this in a more straightforward way, with maybe an easier to understand problem. Let's say we have, I don't know, fish swimming by in a stream, okay? So on average, we expect to see 5 fish in 10 minutes. How many fish do we expect to see in 20 minutes? Right? So if our expectation is 5 fish in 10 minutes, how many fish would we expect in 20 minutes? Yeah, just be 10. How many fish would we expect in 5 minutes? $2.5, yep. And then how many fish would we expect in 15 minutes? Yeah. So it's the same process that's occurring in this problem with 15 cars passing through in 10 minutes, right? What we're getting here is just, this is sort of like a delta, right? This is how much we're going to change the original lambda. And in the first case, if we're considering 10 minutes, then this delta, we can think about it as being 10 over 10, right? So delta sub 1 is going to be 10 minutes over 10 minutes. And this delta, or delta sub 10, delta sub 15 is going to be 15 over 10. This is how we modify. This is how we modify this. So this is 10 minutes over 10 minutes. But of course, we don't need to explicitly do this. It's implicit in that we're describing the expectation for 10 minutes, the average for 10 minutes as 15, right? So essentially, if we're thinking in this, if we're considering 10 minutes, we're thinking 15 cars in 10 minutes. And then we want to think about how many cars in 15 minutes. So the delta here, the delta in the first one is just 1, right? 1 is equal to 10 over 10. 10 minutes over 10 minutes. That's just the identity. That is the one that we're working with, the identity. However, if we're going to modify this, our delta, our change here is going to be, you know, whatever our original was in the denominator, right? You know, dividing into whatever our change is. So 15 minutes over 10 minutes. So we can look at this as 15 delta, or 15 times 15 over 10. So all we're doing here is we're extending the amount of time, right? And that's going to modify the amount of items that we expect to see in that time. Another way to think about this, let's think about a different problem. Let's think about, you know, on average, there are 10 drops of water. Oh, this is not a good example. Yeah, that's not a good example. Let's think about there being, if you're sitting somewhere, there are going to be 7 birds in a given 10 square feet of grass, right? So we want to think about this. This is a tricky one, actually, because we have to modify the lambda in a different way. Let's stick with time, just to keep it less confusing. So 7 birds, you're going to see 7 birds in 20 minutes, right? How many would you expect, on average, how many would you expect to see in 25 minutes, right? How many birds would you expect to see in 25 minutes? Yeah, and how did you figure that out? And that's really the thing. If we're increasing in time, right, from 20 to 25, the way that we can think about this is 7 times 25 over 20, right? Whatever that works out to. It sounds like it's 8.25. And that's really what, that's just a convenient way to, you know, I'm calling this our change in time. I'm calling it a delta because it's a modification of the original. That's the only reason I'm calling it that. But upon changing the amount of time we're considering, we have to change lambda accordingly. So I hope that clears that up. And I think if you do a few more of these problems, it'll become clearer with time, right? So, oh, sorry, 8.75 was it? Either way, it's you know, 7 times 25 over 20, whatever that works out to. And you know, however you calculate that, you know, I have this form of calculating it that maybe it seems obtuse to some people, but you know, that's sort of the way that I think about it. But if you have another way of calculating it that leads you to the same to the correct lambda, that's absolutely valid. So let's get back to the CDF problem, and I'll put 2 minutes on for this, just to get back to it. So, given intersection, we'll have on average 15 cars through in 10 minutes. What is the probability that more than 15 cars will pass through in 15 minutes? let's think about how to solve this. So we can calculate our lambda, right? Pretty directly, I think. That lambda is just going to be the same lambda that we saw before, because we are we are considering the same span of time, 15 minutes, and I will just go ahead and put that in there. Okay, so what is k high here? We're considering more than 15 cars, all right? So we have to be careful about how we think about this. If we have a span of 15 minutes, right, then we're considering the probability of more than 15 cars. And maybe I don't want to think about this in terms of time. I just want to think about this like so. It's going to go on to infinity. So we are going to have 0 cars, 1 car, 2 cars, 3 cars, 4 cars, etc. And then we're going to sort of pivot around 15. We are not actually interested in what the CDF is going to give us directly, which is going to be the probability, the cumulative probability of this. We don't want that. We want the cumulative probability of all of this, exclusive of 15. So, going off into infinity. And the way that we're going to answer that is just by subtracting whatever the probability is that we see here. So we can do 1 minus this CDF with a k high of 15. So let's see what that is. It looks like that's a pretty decent probability, right? 0.936 or 0.937, roughly. Now, let's think about why that might be so high. I think this is a good thing to think about. So what is our lambda? Once we modify it, let's just look at it. Oops, lam is not defined. That makes sense. So we would expect 22.5, and we're asking the probability of 15 or more, right? So if you think about, and we'll think about this a little bit more pretty soon. If you think about these probabilities, somewhere around 22.5, so we've got 22 and 23 as being the most probable, and we're going to have decreasing probability as we go off to the right, and decreasing probability as we go down to 0. And 15 is going to be somewhere over here, right? So if we're thinking about everything past 15, it's going to be the whole rest of this distribution out to infinity, which is going to be, the vast majority of the distribution. It's kind of nice to look at this in the form of a dictionary. I think that ends up being very helpful, and it directly applies to our technical interviews as well. Spelling out the unit. Okay, let's revisit this lambda question for just a moment further. The units in. So, am I understanding correctly that you're looking for the kind of abstract units of lambda? Is that accurate? Not specifically in relation to cars. But in general for lambda. So, yeah. So I think the way that I think about this is that this is in events for time, or events in time, right? So how many events in some span of time. And I kind of leave it at that, to be honest. Well, it could be time, it could be volume or space, and the dimensionality of this, like time is nice because it's, it's just a line. We don't have to worry about modification, based on, say square footage or volume or anything like that in our calculations and our modifications. Yeah. So that's our frequency, right? Events per time is our frequency. Sure. Yeah. Cars by itself is not a rate, but cars in span of time is a rate, right? It's a frequency of the occurrence of cars related to a specific span of time. So that's it's kind of maybe we're in the semantics of this, but we want to think. Yes, what we put in lambda looks like cars, right? But that's not exactly what lambda is. Lambda is going to be the amount of cars. I'm sorry. Yeah, lambda is going to be the amount of cars that we would expect to see pass by in a certain span of time. So that's I think a good way to think about it. Let me drop that solution in the Slack. So about 0.937 or 0.9366. Let's do that. That's the probability we were seeing for the Poisson CDF breakout. Okay. Yeah, I think we often call this a rate or a frequency. We call lambda a rate or a frequency, just because it's the number of events in a certain sort of space. Okay, so let's move forward into something that looks like what you'll see on one of the technical interviews, depending on which one you get. So this is I think a pretty quick breakout. We've done this sort of thing a number of times so far, and you're just going to code a PMF dictionary. Of course, you're going to return a dictionary. You've got three parameters: a lambda, low k, and high k. You want low and high k to be included, right? You're going to hold lambda constant across the whole thing. So I'm going to put 5 minutes on this. Go ahead and code the Poisson Pmf dictionary. So let's code this out really quick. Oops. Oh, I don't like it when I do that. Okay, well, I'll just shrink that down. Okay, so let's code this PMF, this Poisson Pmf function. This is going to look like the PMFs that we've written already. The PMF dictionaries that we have written already, that is. So let's look at Poisson Pmf Dictionary. And we've got three parameters. We've got lambda, we've got low k, and we've got high k. So this is going to be just that pattern where we traverse the dictionary and we fill it in. So we've got our dictionary, and we're going to say for k in range, we're going to go from low k up to high k plus 1. And this is going to get us a view of the probabilities for a range of k values. So d sub k is going to be the Poisson Pmf, where we pass in lambda and k, and we return the dictionary. So if I call this, so here's our dictionary, and we can traverse this lambda. Let's reference that problem really quick. So we're referencing the cars problem. Our lambda is going to be, what was it, 22.5 cars in 15 minutes, right? 22.5 cars every 15 minutes. Our low k, let's set that at 10. Well, let's look at 0. And let's set our high k at 30. And we'll just see what we get with that. So I'll say for key value in d.items, let us print an f string of the key and the value. Okay. So these are the probabilities for a certain number of cars every 15 minutes. So if our expectation is 22.5 cars in 15 minutes, notice that 22 and 23 are our most likely outcomes, but not by a whole lot, right? In fact, 21 and 23 are going to have near equal probabilities, but we can see, you know, if our expectation is 22.5, 22 is going to be our sort of modal outcome. And we can see for 0 cars, it's very unlikely, it's very improbable that we're going to see 0 cars. It stays very improbable for quite a while. And then we get into this realm of, well, maybe 13 cars, there's a 1% chance, 14 cars, 1% chance, 18 cars, some close to a 6% chance. And we get to this peak around 22, and then we start declining again as we go on. And if I were to set this to 40, I think we'd see quite a bit of decline by the time we get out to the probability of 40 cars passing by, right? So it's going to get, we have kind of a rounded, a distribution that has a peak around the mean. And I think that's not too surprising. I think that seems reasonable. If we expect to see 22.5 cars in 15 minutes, then we're likely, to see declining probabilities going to the right of that, or higher than that number, and declining probabilities going lower than that number. We're not likely to see other peaks. That's not what we would expect to see in the sort of idealized Poisson. So I think the Poisson dictionary is a good way to look at Poisson. Gives us a fairly reasonable view into the shape of the distribution. Oh. Okay. Sorry, I'm just following up on this. Following back up on this breakout. a given intersection will have, on average, 15 cars pass through in 10 minutes. What is the probability that more than 15 cars pass through? Let's look at the earlier breakout. I think it sounds like maybe there's some confusing language in there. So 15 cars in 10 minutes. So 15 cars per 10 minutes, and we're asking the probability of 20 cars in 15 minutes. And what's happening there, right, is just this change from 10 minutes to 15 minutes, which implies that this 15 as a lambda needs to change as well. We're going to modify that accordingly. But but lambda, exactly. So I think I understand the confusion here. What is the probability that 20 cars pass through in 15 minutes? Well, what we don't know in this moment, when we're first reading this, what we don't know in this question, we don't know what lambda should be. Because our lambda is defined right here. Our lambda is 15 cars in 10 minutes, but we need to recalculate that in light of 15 minutes, right? So I can see, maybe there's confusion in that. This is our value of k, right? So 20 doesn't figure into that. 20 isn't part of the calculation of lambda at all. That's the k for which we're looking for the probability. Let's see. Yeah, we don't know what lambda should be yet, but we know we have enough information to determine a new lambda, and that's one of the things about the Poisson distribution. If we have an expectation for a certain amount of time, then we can calculate a new expectation. And I think that's kind of an amazing thing about Poisson, right? Where, if we think about this in terms of photos of stars, right? If we have these celestial photos, and on average, we would expect to see 20 stars in one photo, right? That's what we would expect to see. How many stars would we expect to see in 2 photos, right? So I think that's pretty clear. We would expect to see 40 stars in 2 photos. However, what we're asking with the Poisson Pmf in most cases, okay, well, we expect to see 20 stars or we expect to see 40 stars. What's the probability of seeing some other number of stars? And so, that's the general format of these. We're extrapolating out a different probability for a different number, or maybe even the probability of lambda itself, but more often the probability of something that's not lambda. Okay, we can come back to this during questions at the end. All right, so we'll skip the last breakout in this. It's just coding a Poisson Cdf function, and I think we've seen that. A Poisson Cdf dictionary function. I think that's something that we would generally know how to do. I'm going to just show one last aspect of this. So we have this dictionary of probabilities, right? We've got a dictionary of probabilities. Now, what if we are trying to get a dictionary of counts based on those probabilities? How might we do that? It turns out that's not that hard to do. We want to think about a number of observations. we're trying to imagine an idealized form of this, so the number of observations for that we're going to make, if we believe that this phenomenon follows a Poisson distribution, and we do say 10,000 observations, we're going to be able to multiply 10,000 by the probability in order to see ultimately some theoretical counts of observations, right? Now, this is reflecting what we might see if we do 10,000 observations, then we do 10,000 observations again, and then we do 10,000 observations again, and so on and so on. And then average all those together, sort of like what we did with the binomial distribution when we were doing sampling. But this is kind of in reverse. And what I'm going to do here, I'm just going to round these, and I want to point out something in terms of observing Poisson phenomena in the real world. Notice we're zeroing out. We're zeroing out unlikely, Poisson events. So it's very unlikely that we're going to see 6 events in this span of time. It's very unlikely we're going to see 3 events in this span of time. So we aren't likely to observe those within 10,000 observations. And what we can notice here though is that we have a theoretical set of counts if the phenomenon perfectly follows a Poisson distribution, and we average all of our trials of 10,000 observations. So that's just something to keep in mind. We don't always have to go from counts to probabilities. We can go from probabilities to counts as we're doing here, just by multiplying by a number of observations. So keep that in mind. That comes back up at various times. That might even come up in the interview. So let's take a short break. Let's take, So we'll wrap Poisson there, and we can talk more about Poisson at the end of class. And it might be a good thing to cover in study hall. So let's take a 6-minute break, and when we get back, let's look at continuous distributions. We're going to look at a couple continuous distributions, and we're going to kind of touch on some light calculus, but from a fairly procedural point of view, not doing calculus by hand necessarily. Okay, I'll see y'all back here in 6 minutes. All right, so let's get back. We'll start off. We're going to start actually into some continuous distributions. And we're going to think about these in a couple ways. We're going to skip some of the slides as they're not so relevant to the technical interview, and I haven't fully revised them yet. But we can focus in on a couple maybe interesting things here. So I'll go ahead and let's see. I'll minimize that and just open up a new instance. So we're going to think about three continuous distributions, one of which will go into some depth. We might go into normal depending on the amount of time we have, but I mainly want to focus on the uniform distribution. And I want to show you a scheme for applying what I'm going to call a geometric decay to a binomial process. So let's think about that. All right, so we'll start with uniform, and we'll go from there, and we'll see how much time we have for the normal distribution. I do think there's an interesting thing we can do with the normal distribution, and I would like to do that. I would like to get to that if we can. All right, so just like we had a discrete uniform distribution, we have a continuous uniform distribution. And let's say this is between the values 0 and 1. Now, something that is kind of special about this is, let's say we have a number 0.63, or let's say that's around 0.63. If this is a uniform distribution, what is the probability of drawing a number between 0 and 1 that is less than 0.63? So what is the probability that x is going to be less than 0.63? What do you think about that? So if every possible number between 0 and 1 has equal probability of being drawn, what is the probability of drawing a number less than 0.63? Well, we can code through a scheme that will actually show this, and we can also think about this as being 1 arbitrarily, but the main point here is that every possible value has equal probability. The probability of x1 is the same as the probability of x4, and so on. Every possible drawn value has equal probability in a uniform distribution. So, this gets a little bit tricky, because we're dealing with something that is continuous, and we want to think about it as being purely continuous, but we're going to think of every possible value as having equal probability. So maybe it's better to show this in code where this ends up. That said, maybe we can think about a different question in regards to this. So there are infinitely many possible values, possible numbers between 0 and 1, right? If we're thinking in a continuous way. what is the probability of a specific infinitely precise number, right? Like let's say 0.31972 and so on. What is the probability of this? Remember, this is infinitely precise. What do you think is the probability of getting that? Yeah, exactly. It's this is about as close to 0 as we can get, right? Because this is going to be an infinitely precise number, right? Some infinitely precise number over infinity, and anything, anything divided by infinity is going to be as close to 0 as we can think about. And so, backing that up, we can't just find the probability of a specific value. The probability of a specific value in a continuous distribution is going to be 0. That's the way we're going to think about it, at least. So if we are considering, but we can, however, figure out probability within a range, right? So what is the probability that x is going to be less than 0.63? I saw somebody throw that in the Slack. That's actually going to be 0.63. Okay? That's what that's going to be. And if we wanted to verify that to ourselves, we could break this into ranges. We could say that 2, 3, 4, 5. Oh, that's not very evenly divided, but 1, 2, 3, 4, 5, 6. Let's say that's evenly divided. We could think about each of these as, this is 0.1, this is 0.1, this is 0.1, this is 0.1. The width of this is being 0.1 multiplied by 1, right? So 0.1 times 1 plus 0.1 times 1 plus 0.1 times 1 plus 0.1, 6 times plus 0.03 times 1. And so we can construct this area by sort of taking a divide and conquer approach. The nice thing about uniform is that if we are asking this question, what is the probability that something is less than a specific value, if we have a lower bound on this, let's say 0, then that probability is just going to be that number. The probability that x is less than 0.63 is actually going to be 0.63. So that's nice. That's a very convenient thing in a continuous uniform distribution. So as we had PMFs for discrete distributions, we have PDFs, probability distribution functions, for continuous distributions. PDFs don't give us a probability for a distinct value. They give probabilities over an interval. So this is a probability over an interval. Now, why is that? Well, if we're trying to get a distinct probability, a probability for a distinct, infinitely precise number, as we, already said, that's going to be 0. So we have to bound that number in some way. The PDF is going to give us a bound for that number. Now, when we look at this kind of in relation to the normal distribution, we might think about it a bit differently. We might see the PDF as giving us, if we ask for the PDF of this value x, we're actually going to get the height on this plot at that point. So we're going to get the height of the normal distribution at that location. So that's something like a probability over an interval, but I think to me it's much more clear to think about this as that's getting us the height of a point on the curve. And so we can end up utilizing that, and we will. Hopefully, we'll get to that in a little bit. Okay, so I don't know why that's doing that. Let's try that again. Sorry, sometimes my drawing program gets a little buggy. There we go. I don't think that should happen again. All right. So, you know, I'm going to speak more generally. I kind of hinted at this with uniform distribution, but I want to speak more generally about distributions. If we are trying to understand the probability for a range of outcomes, okay? And let's say we're trying to figure out the probability for all outcomes from 0 up until x. We can make an assumption that the entire area under the curve of this, so the entire area under the curve, right, from negative infinity to positive infinity, so that whole thing is going to equal 1, okay? If we assume that, then we can think of a subset of that area under the curve as A, and we can consider the area of A as being a probability of getting a value in the range, in this case from negative infinity to x. Now, how do we calculate this area? It turns out that that's not that easy. If we're considering you know, calculus in general, then we might perform integration. We might perform integration in such a way that it's kind of a procedural approach, procedural mathematical approach. It turns out that the PDF for the normal distribution is not very calculable, and that's a little bit of a frustration. And so we take a different, we might take a different strategy. In this case, we might, just like I was showing with the with the uniform distribution, we might cut this up into rectangles and get the area of these rectangles. That's an approach we can take. Now, I'm mentioning this in reference to the normal distribution, but we can think about this for any distribution. Like, let's say I'm just going to make up a distribution here, and let's say it looks like this. Okay? And if we're trying to figure out the probability of some value, some value between you know, x1 and x2, then what we can do is get the length here and get the height here, right? So we can get the width and the height, or length and the height, however you want to call that. And we can simply draw rectangles and sum the areas of these rectangles. This is going to be an estimation. And we call this estimation by Riemann sums. So Riemann sums. This is an estimation. It's not going to get us an exact answer. And that's important to remember. But also it's important to remember that we can do things in a procedural way, and we can approach a better probability if we make these rectangles skinnier. And if we can make them infinitely skinny, our estimation is going to approach the actual area. You know, practically we can't do that. There are mathematical ways of doing that on a lot of functions. And then some functions we cannot integrate. It turns out the normal PDF is a function that we can't integrate. But we can perform an estimation by Riemann sums, which we'll try to get to in a little bit. So let's get back to the uniform continuous distribution. And I want to show you something a little bit funny. And this is a procedural way to get a random number from a uniform distribution. So let's say from random, import choice, and we'll do get bit, and we'll return a choice between 0 and 1. Okay? And then we'll get some binary, right? This might look very familiar because I wrote this just a couple days ago. I may have actually written this yesterday, if I think about it. So I'll write a comprehension here. So I'm going to get a bit for whatever in range n. And this should get us a list of bits. So if we print get binary at this point, we should get 8 bits of binary. Oops. Okay. So that's 8 bits of binary. That's fine. It's different every time we run it. Now, here's a question. Is any one of these lists of binary more likely than any other list of binary? And I don't mean the count of ones. I mean any given outcome here. Is any given outcome more likely? No. No, they're all equally likely. These are a series of independent trials, and one trial doesn't affect the other, so any given binary word is going to be equally likely to any other binary word. It turns out we can process these. So I'm going to get some binary out of get binary, and we'll make it of length 8, why not? And I'm going to make an accumulator. I'm going to start it at 0. And what I'm going to do is give a weight to each bit, okay? So the first bit, binary sub 1, or sub 0, I'm sorry, is going to get the weight 0.5 to the first power, okay? And I'm going to take binary sub 1 and multiply that by 0.5 to the second power. And I can keep doing this, right? I can do this 8 times. You might be thinking there's an easier way that you could do this, because this does seem pretty much a procedure that, you know, maybe there's an easier way than writing all of this out. But I just want to show you what this does. So that's let's see, 4, 5. This will be 6, 7. That's it, actually, right? Because we're 0 indexed. Okay. So if I print this, what do you think we're going to get? What are you expecting that we'll see here? So we might see 1, but here's the thing: we can't actually see 1, unfortunately. If these were all 1s, if the binary, and I'll just show you what I mean by this. Let's say we have 8 1s, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yep. Okay. If I run this, we get 2.25. Now, why is that? 0.5 to the first power, 0.5 to the second, 0.5. Oh, I'm sorry. First power, second power, I forgot to update the powers. Third power, fourth power, fifth power, sixth power. This is very important. Sorry for forgetting that. Seventh power and eighth power. Okay. So now, let's see what we get. We get 0.996. Now, we could get closer to 1, right? We could put another bit on this, and we could process this to the 9th power, and we're going to inch our result toward 1. But the thing I want to point out here is that these first two bits, so this first bit, if we're randomly generating binary, is either going to be 0.5 or it's not. And the second bit, when we multiply it by 0.5 to the second power, which is going to be 0.25, is either going to add 0.25 or it's not. So what's going to happen here if we get this random binary? This is actually a uniformly generated number that we're seeing out here. There is no number that is more probable than any other number. However, we can't get we can't get 1, and we theoretically can't get 1. Even if we can get 1 only if we run out of precision on our computer and we roll over to 1.0 or something like that. That's the only way that we're going to get 1. So this is, if you're thinking, well, where am I going to see kind of, what is varying the outputs? The outputs are being varied because there is a random call, or there's a function to get binary, which is calling to get bit, which populates a list of bits with 1s and 0s randomly. So we're sampling from, we're building lists of random binary, and then we're processing that random binary like so. In this case, the positional, we're taking each bit and multiplying it by 0.5 raised to the positional value, or 0.5 raised to the first power because that's the first bit, 0.5 raised to the second power for the second bit, and so on. Okay, yeah, so let's think about this in terms of some binary. So 1, 0, 1, 1, 0, 1, 1. This is going to get multiplied by 0.5 to the first, okay? This is going to get multiplied by 0.25, 0.25, not, I'll just do this. So 0.25, which is 0.5 to the second, right? 0.125, which is 0.5 to the third, and 0.5 to the fourth, right? 0.5 to the fifth, and so on. So that means this is either going to accumulate 0.5 or it's going to accumulate 0. This is either going to accumulate 0.25 or it's going to accumulate 0, and as we can see, the 1 is acting as a switch. The leftmost bit is multiplied by 0.5 to the first power in this case. So this is a scheme to transform a binomial process, right, where we're generating 1s and 0s, and turn it into a uniform distribution. The idea here is to think about this as kind of an algorithm out in the wild, okay? Like, we are trying to develop an understanding of where a distribution comes from. And so, looking at this, we are generating a uniform distribution. We are pulling random 1s and 0s, and with this scheme, we can get a random float that is between 0 and 1, although we can never get 1 explicitly. We can get 0 if we draw all 0s. Why in this case is it 0.5 to the power 1, 2, 3, as opposed to what? We could arbitrarily select different powers, but that's going to change our range, right? So we could do 0.4 to the first, 0.4 to the second, 0.4 to the third, and so on. And that's going to give us a different uniform distribution. This is going to be a uniform distribution between 0 and 1. Because we don't care about the binary. We're not converting from binary to decimal. We're converting from a randomly generated binary list into a uniformly random float between 0 and 1. So what we're doing is sort of explicating a phenomenon to generate random numbers. Yeah, exactly. Yeah, that makes sense. That makes sense. And when we were doing decimal counting with binary, that was for the basis of being able to generate an arbitrary length binary list for the purpose of, say, building binomial distributions. But binomial distributions are not related to decimal in that sense. They're just using a binomial process under the hood. So I'm showing here that here we've got a uniform distribution that's using a binomial process under the hood. And so a lot of these things kind of relate back to something more primal, like zeros and ones. When Leibniz sort of, I don't want to say Leibniz invented binary, but Leibniz ideated around binary and was like, oh, this is going to be a big deal, right? And it turns out we can root so many things into binary. We can root these discrete distributions like binomial, Poisson, and geometric. We didn't cover geometric, but geometric goes right back to binary. We can root those into binary. We can also root a uniform distribution into binary, which is pretty compelling, I think. It's a compelling reason to dig into binary and kind of look at it from a number of different lenses. So that's kind of a basis for understanding a bit of a uniform distribution. What that might, how that might exist under the hood. So one thing I would like to dig into with more depth is the normal distribution. I don't think we'll have enough time for that today, but I think we can cover exponential. I believe I did paste the code, but I can paste it again. So this is not exactly how your computer generates random floats. That's a whole other algorithm that I am going to choose not to get into today because it's better to think about it through assembly. And I don't think any of us want to mess with assembly anytime soon. But there are various ways of generating randomness, uniform randomness, normal randomness, and a variety of other kinds of randomness, as it turns out. It's sort of nice to think of random as being something that comes out of a distribution. And when we think of random, we think sort of this sort of purely random, but really we're talking about uniform random when we say that. If we talk about something as being normal random, then it's much more likely that we're going to pull a number close to the mean, and less likely that we're going to pull a number further away from the mean, right, in either direction. So that's a different kind of random. Is it still random? Yes, it's a type of random. So we're kind of diversifying part of the idea of what random is when we're looking at distributions. Good question. Yeah, let's look at that. So it seems like we have 8 bits from bit 0 to bit 7. This is based in Python's indexing. Python uses zero-based indexing. But we can think about this as being 1 minus 1, and this being 2 minus 1, right? If this is our first bit, when we're thinking about it in a list, our first bit is the 0 index. And so this is one of those places where Python, the Python syntax sort of doesn't match the way we think about things, right? So the first bit is actually the 0th bit in Python, but in this process we're going to exponentiate to the first power. So that's where that relationship is. That's why we're using indexing from 0 to 7 and exponentiation from 1 to 8. What kind of endianness? The way that, if we're thinking about endianness in this sense, we're starting with the leftmost bit, and we're applying the most weight to that. We could start with the rightmost bit and do that instead, but I think this scheme lends itself better to thinking in left to right, because then we're taking a random draw every time. And if we were to take infinitely many random draws, we're going to build an infinitely precise random number, a random float. Yeah, we're reading them from left to right. Yep. Okay, so let's think about exponential. And exponential, the main thing that I want you to take away from exponential, and this is not to belittle or diminish the exponential distribution at all, but the main takeaway I want you to have, and this can apply to the Poisson interview that you might receive, or an interview that we have that covers Poisson. We can think about the exponential distribution as modeling time between Poisson events. So let's root that in time. I think it's helpful to root this in time. These sort of continuous distributions lend themselves fairly well to time. If we have a span of time, let's do the same, I don't need to do that, 0 to 10, and we have a lambda of 5, where we're considering, on average, we're going to see 5 events in 10 minutes, let's say, or 10 units, whatever that is, but let's say 10 minutes. How do we expect those to be spaced, right? So that's a curiosity. And it's not quite so simple as evenly spacing them. We know that's not what happens in the natural world all the time. Is that what we would expect to happen? Well, I think that depends. So we can answer certain kinds of questions with the exponential distribution. We can answer questions like the time you might expect to wait for, let's say this is five taxis in 10 minutes. Well, how long would you expect to wait for a taxi if there's 5 taxis every 10 minutes? I think that one's pretty intuitive, right? We're thinking a taxi every 2 minutes, probably. Your expected wait time is probably 2 minutes. Now, the thing that we're modeling here is if we have an event, right, just to be very clear, we're modeling the probability of a certain amount of time between Poisson events. So that's something the exponential distribution can tell us. There are a lot of different ways of thinking about and defining exponential, but we're going to think about it specifically this way because it relates, that's how we cover it in our materials mostly. So there are some formulas in relation to the exponential distribution, and I'll kind of code these out. So we've got a PDF, we've got a CDF, we have a mean function, we have a variance function, and of course, if we have variance, we have standard deviation. So I'm going to code these out really fast, and we're going to, kind of think about these. I'll share them, and why don't I also bring up here the formulas themselves in their mathematical notation. I think that could be helpful. So we have a PDF, we have a CDF, and notice in this CDF we're not accumulating, right? We have a much more friendly CDF here than you might expect, and we have a mean function. I'll just put this behind the PDF, so we'll get to it in a little bit, and we have a variance function. So we're going to import some things. We need E for this. So I'm going to say from math, let's import E. And I'm also going to import the square root function because we'll use that for the standard deviation, which is just the square root of the variance, right? I like using square root instead of exponentiating to the 0.5. Either way is fine. Square root function is just slightly faster, but it doesn't really matter. Okay, so let's look at this exponential PDF first. And once this is written, we'll look at a problem. So lambda and x are inputs to this. If x is less than 0, we're going to return 0. Now, just philosophically, think about this line. If x is less than 0, return 0. If we're looking for the probability of an amount of time less than 0, negative time, what is that? We don't really have that. So we're going to just throw that away. We're going to assume there is no probability of negative time. Oops. And then we can just return lambda multiplied by e to the negative lambda. And that is going to be multiplied by x. Okay. So the exponential CDF is very close to the PDF. So I'm just going to slightly modify this. And we'll say lambda, this is just 1 minus e to the negative lambda times x. All right. And the mean is very straightforward, right? This is just going to be 1 divided by lambda. And then finally we have the variance. So exponential variance is going to be 1 over lambda squared. And then if we want the standard deviation, this is just going to be the square root of that. All right. Okay, so here we have these formulas. And we want to consider, at this point... Oh, thanks. Let's just make sure that those are all working as expected. And import square root. Okay, that should be good. So we have these formulas, and we want to, just think about these in the context of their use. So I think I have a breakout here. And I think this is a very classic kind of problem. We're going to think about taxis. And we'll go through this kind of one by one. So this is sort of like a hashed lambda, but that just means lambda. That's all that is. It's a lambda. It's 0.1 cabs every minute is how we're thinking about that lambda. So what's the probability that you'll have to wait more than 10 minutes? Okay. So offhand, what kind of problem is this? What kind of function are you going to use to answer a question like, what's the probability you'll have to wait more than 10 minutes or less than 3 minutes? Yeah, that's a CDF problem. Exactly. So how do we start thinking about answering this? It turns out this is very similar to what we've done with discrete distributions, and we can utilize these functions pretty directly. So what does that look like? This is just going to be the exponential CDF, right? Where we set our lambda to 0.1. That's our probability per minute. And then we're going to feed in x, and x is representative, in this case, of time. Okay? So what we're thinking about here, and what this is actually going to tell us, we're thinking about this in terms of 10 minutes. What's the probability in relation to 10 minutes. In this current form, this is going to answer the question, what is the probability you'll have to wait 10 or less minutes for a cab? That's what this is answering. But the question is, what's the probability you'll have to wait more than 10 minutes? So we just want to, oops, that should be x. We just want to wrap this, we want to get the complement of this. So if we expect a cab every 10 minutes, what's the probability of, waiting more than 10 minutes? If we look at this, looks like that's 0.367 or 0.368 roughly. So we are much more likely to see a cab within 10 minutes if we're seeing 0.1 cabs every minute. So let's just put that result in, 0.368. Okay, so let's think about these other questions. What is the amount of time that you would expect to wait? Well, expectation here, what's synonymous with expectation? What do we think of when we think of expectation? Turns out we think of the mean for expectation. Often we'll use those two words interchangeably, and that might get confusing, I know, with lambda, because lambda is an average expected number of events. But we're considering the time, right? What is the expected amount of time in this case? So if we have a lambda of 5, and we're trying to consider, let's look at that formula for mean. That's going to be 1 over lambda. What is our lambda? It's 0.1, right? And if we notice this problem statement, we expect cab arrivals to be 0.1 per minute. And if it's 0.1 per minute, at what point do we have a probability of 1? Well, I think that's obvious. We have that at 10 minutes. And so I think our expectation here is going to be, well, let me actually put in, wait, what is going on there? Oh, because it's not a lambda of 5, I'm sorry. It's a lambda of 0.1, that's why. 10 minutes. So that makes sense. Our expectation here is that we're going to wait 10 minutes for a cab. And let's take that a little bit further. What is the variance? Well, we can describe the variance, but I would prefer here to describe the standard deviation, right? Because the standard deviation is going to be in units that we understand. Our standard deviation is in units we understand. We're going to be waiting, we would expect to wait 10 minutes, give or take 10 minutes. Okay? So that, if we were thinking about the variance, well, what is the variance telling us? It's telling us time squared. Time squared is not that easy to interpret, and if it's time squared, that's going to be 100. So I think in so many cases where we're looking at variance, we're probably going to want to rethink that in terms of standard deviation, just so that we can interpret it more easily. Not all the time, depends on what domain you're in, but again, it's nicer to have it in the units and not the squared units. So I'll just drop these in, and I'll relate that directly to this. You might get, say, a question, where we give you these formulas and we ask you to, write the exponential Pmf, write the exponential Cdf, write the exponential mean, and we'll give you all the formulas and the information, and then we might ask you questions that are, that look like this, where, how long would you expect to wait, or something like that. Exactly. That's exactly how I visualize variance. squared minutes. I find that hard to visualize, to be quite honest. And in most cases, so I relate this back to square feet in a room. It's much easier for me to think about a room in terms of its length and width dimensions and describe it that way than it is to conceptualize square footage. When I think about square footage, I have to take the square root in my head and try to imagine how much area that is, and that's much harder for me to do offhand, right? Especially for an oddly shaped room. And for most places where I might use variance, I'll probably end up using standard deviation. So let's stop there.